Greetings, I'm Yousefzadeh, and in this video we are going to talk about the different kind of processes that we have. And nowadays data science people hear a lot about different processes other than CPUs. They are using GPUs for training their models, they know that they are better, and also these days they may have heard a lot about words like FPGA, about accelerators. In this video, we aim at deciphering these words and why processors like GPU, FPGA, and accelerators can be faster than CPUs. We will review this content together, starting with computing. Computing is using the computer technology to complete a goal-oriented task. Goal-oriented task is an algorithm. We know about that. And also we have to recall that computing is transferring the input data into output data. And according to the famous saying from Richard Hamming, the purpose of computation or computing is gaining knowledge, is gaining insight. We are going to have insight after processing our raw data to end up in better, more efficient decisions. But processes as the elements that make computing possible. So we have seen that we have different processes. We have heard about them. Most of us have heard about GPUs, about CPUs, FPGAs, and accelerators. But why do we have them? The reason is that they are the devices that make computing feasible, make it possible. So the upcoming question is that how they are making computation possible. It's from one side it's simple because they are making electrons working for us, but how? In this video we are going to answer this question by looking at the transformation hierarchy. This hierarchy is the hierarchy or it is the concept that makes processes to make process to be able to make electrons to do the computation to work for us. But how? We are going to state our problem, pass it to the lower levels. It is handed to electrons that they can easily understand and do the work for us. The whole story is not like that, but it is the hierarchy that makes engineering of the systems easier, and because of that we are looking at it in this way. So starting with problem, when we have a problem like calculating the first n numbers or training the image classifier, a binary or multi-class thing, even if we are going to tell somebody that is not from computer science or specifically not from machine learning data science side, if we tell them that we want to train a binary image classifier for cat and non-cat images, they won't say, I don't know what you are talking about. And also if we go to some normal people and say that we want to calculate the n first number of a Fibonacci series, they will ask you what Fibonacci series is. So we have to add more details to the problem. And this is where we have algorithms that we know algorithms are the well-structured, organized, definite number of instructions, and this flowchart shows the algorithm for the Fibonacci series. But when we want to give it as something instructable for computers, we are going to state them in a language. And here you can see that we stated the Fibonacci series algorithm in Python, here in C++. But how they are going to be handed to processes? Should we translate themselves? Should we translate these high-level languages to the processes or what? We can do that, but it will be very time-consuming and not possible most of the time. We will make a lot of errors, and sometimes when the source code gets so large, it becomes impossible. So we have software, we have system software in between the program and the architecture or the processor. That makes it possible. We are using compilers to translate our high-level program to the language of the processor. And here the program is translated to the language of the processor that we know. For Intel's it is like x86, for also for AMD processors and Intel processors it is 86, it is x86. For ARM processors it is a risk that they are using MIPS language. For GPUs, for NVIDIA ones it is CUDA, for AMD it is another language. So the system software is going to ease our speaking process to these processes, to these devices. If we come a level lower than the architecture, we reach microarchitecture. That in this level we can see that how processor is built and how it is implementing these languages that we had in architecture level. Because in architecture level we were telling the process to do an add, to add two registers, to add two operands together, and they are how implemented in the hardware, in the CPU hardware. You can see here we have cores, we have embedded embedded GPU that is on one single die alongside the CPU, and also other components of the processor. But the next level is that how this processor is implemented. So we reach the logic level, that in this level people have implemented the basic operations, basic components in logic level. Like if you look at this specific language, it is the simplest example of how this layer is built up, is that you want to sum up two bits. So this table that's called truth table, you are going to list different possibilities, like these one, like 0 and 0 ends in 0, 0 and 1 ends in 1, also 1, and when it's 1 and 1 it ends in 0 with a carry. So we can build this sum with XO, because the output is 1 when we just have 1 1, and for the carry we can see that we have 1 when both of the D1 and 2 and D2 are 1. So this level is in logic level. But how this logic is built? It is built with electronic devices that in computers, in hardware, transistor works as a switch, which is the primary element that we have, and other devices are also integrated, but not like these. But you know, the basic is electronics, is digital electronics, and these devices are the components that make it possible that process is going to make electrons to work, to do the computation, to make them flow. And the simplest example is that we were using electrons for illumination, that they were heating the atoms of this specific metal inside the bulb to produce light. So we saw that how processes made computation possible by talking to electrons. But we saw that we have different processors like CPU, GPU, FPGA, and accelerators. But what are the reasons we have these? It is because of the trade-off that these processors offer. So because of them, we are going to have these different processes. If we look at this table, in this table I try to summarize the trade-offs, something that they offer compared to each other. So we are going to know why these processes exist. If we look at from programmability side, CPUs are easily programmable because we can write programs with CPU without having any harsh problem. You can pick a language like Python, C++, C#, F#, anything you like. You can develop it and give your program to CPU to execute it for you. But when it comes to GPU, It is very common that most of the people that they are not doing parallel computing, they are not writing something for something executable for GPUs, because they know that they have to use CUDA for writing programs, or OpenCL, that they are not very common languages and people, most of them, don't know about them. So the programmability is medium. But when it comes to FPGAs, field programmable gate arrays, it is harder, because people should know about digital electronic basics, and also they have to learn other languages like Verilog. They have to learn how to describe a language, because it's not programming. You are not writing down instructions and you don't expect them to execute one after each other. And when it comes to accelerators, the programmability is much harder, because you have to go open its white paper, know how to write instructions if you are going to write instruction, or how to feed the input and get your output. But from the goal program, the meaning from goal program is that what kind of program these processes are specialists at executing them. When we hear CPU, they are latency oriented. We mean that CPUs are well at executing programs in a fast way. They are very good at executing one instruction at a time very fast. But GPUs, they are good for throughput oriented programs. We mean that they are good in tasks like graphical or image processing things. They can process the whole pixels of an image very fast, because they launch all of the threads at the same time. But the FPGA, because the designer, because the programmer is going to specify what kind of application he is going to run on it, he can determine it. And also for the accelerator, the designer, the architect is going to determine this one. And from the flexibility, how many different algorithms or programs you can write. For CPUs, you can open just a file, a Python file, program it, and you can code exactly what you want. You can change it from a neural network to something very sequential like Fibonacci number, to image processing, whatever you like. But when it comes to GPUs, we have here that it's better for something that they are parallel in nature. So it decreases. It's not comparable to CPU, because you can write a lot of programs there, but here it's not possible. And for FPGAs, it is low, because if you are going to use FPGA, you have to program its fuses, the hardware fuses that you are going to specify, the circuit you are going exactly to build your hardware inside the FPGA. So it is low, and whenever you want to change this one, the programmed hardware, you have to erase it and you have to build another hardware. And for the accelerators, it is super low. Accelerator is going to receive input from you and produce the output, and most of the time they are fixed. But the architect, the designer of the accelerator can play around and provide flexibility if they need. Anyway, it's not something that hard-coded here. It can be flexible somehow based on what the designer or the architect is decided. And the promised performance of this process is that CPU offers fair performance. It's good for some programs, but when it comes to something very parallel or parallel by nature, it's going to serialize it. So yeah, it wouldn't be good. And that's the reason why these days for neural networks, because they are parallel by nature, CPUs are not preferred, and GPUs are the main processes for training of deep learning models. But when it comes to FPGAs, the promised performance is high, because you are building your program as a hardware inside FPGA. You are building the circuit, you are connecting every component. You are not going to do computation for doing computation, because in CPU and GPU you are doing more operations, you are making electrons to run more distances to do exactly what you want. But here you are just making electrons to run for your specific program. But anyway, you know, you have to change every time you want to have another program, and it takes more effort than these ones. And when it comes to accelerator, promised performance is even higher, because in these ones we have to make electrons to run more, and in this one we have circuits inside FPGA that they can vary. The distances can be vary, and how they are routed on the FPGA, because it is offering flexibility. But this one is built in the way that CPU and GPU circuits are built, so it offers super high performance. So in this table we saw the trade-offs, and we could understand why we have these different processes and how they are trading off programmability, the gold program, flexibility, and the performance. So we saw the different processes and reasons. So we are going to start looking more into CPU, GPU, FPGA, accelerator. We are starting with CPU here. When we see CPU, CPU stands for Central Processing Unit. We have to remember three things about CPU: that it is sequential processor, it is latency-oriented processor, it is good for programs that we expect the instructions to be executed one after each other, and the other thing is that they are working at higher frequency compared to GPU. And the powerful processors are Intel's Xeons and AMD's Epics. These are examples, but here we are going to review together the basic CPU, one core, very basic CPU, how it works, because it will give you the idea how it's working. CPU, it fetches one instruction from its memory, it decodes it, then it collects the operands. In decode, it's going to specify what is the operation and the operands, and here it is going to collect the operands. The operands can be on the memory or can be on its registers. Then it's going to execute. It fetched the instruction, decoded and knew what kind of operation, like multiply, add, subtraction, what it's gonna do, and then it's going to collect the operands to bring into arithmetic logic unit. Then it's going to execute. It's going to accomplish the adding on the operands. Then it's going to write it back to memory or to keep it on its registers. So we know that how CPU is going to execute instruction by instruction. So let's look at it from this side. That's when we are writing a program in C language, it is going to be compiled by a GCC compiler, and it is going to be stored on the memory of the processor. Then processor on fetch is going to bring this line, that is an instruction we assume, inside its control unit. Then it's going to decode to specify, to know that what kind of operation it should do on operands. Then in this step it's going to collect the operands from the RAM, from its memory or from its register, then execute it, then it write it back to its registers or to the specific location in memory. But that was the basic processor. These days we have very sophisticated processors, sophisticated CPUs, that they are very good at executing, and that's because people like Hennessy Patterson, Yale, Pat Tomasello, they spent their whole life to make CPUs to work faster, to work in a more parallel way than the basic process that we saw together in the previous slide. Some of the techniques that they are used in modern CPUs are like, they are not just fetching and executing one instruction at a time. they are fetching and executing more than one instruction, that they are calling it a window of instructions, which offers higher throughput. And they are using other advanced hardware execution mechanisms like what Professor Yilpat proposed, like branch prediction unit or out of order execution unit. And also modern processors employ cache hierarchy because of the performance gap that we had between processors and memory technology. They are using temporal and spatial locality to build this hierarchy between the processor and the memory. And also they are employing more cores that current modern CPUs are in the realm of parallel computing, kinda, if the programmer is going to use more than one thread in their program. And cache hierarchy that we talked about as a technique that is going to cover the gap between CPU and RAM or the memory is like that. It is going to use fast and small and expensive memory near to the CPU to cover the latency that the RAM is going to offer on feeding the data. So as we move higher in this hierarchy, closer to the CPU, we can see that we have less access latency. We are getting data from here faster than these ones. And also here we have less storage capacity, and also we have more expensive memory per bit, and also we have more data locality. You can look at spatial and temporal locality if you want to know more about them, but the general is that for temporal locality we say that if we are going to access this location of memory, we are going to access it in a near future. So it's better to have it here. Maybe our program is going to use it. And a special locality says that if you are going to use this location, maybe we are going to use this location too. So it's better to have it here too. And that is the idea of using locality for having caches, faster memories, smaller memories closer to the processor. Pipelining is another basic technique that it's better to know about that, and we will give you a basic idea about how pipelining works. Let's consider this scenario that we have our basic process and we have 3 instructions that's going to execute based on the execution cycle that we saw together earlier in the previous slides. It's going to, for instruction 1, it is going to fetch, decode, collect the operands, then it's going to execute and write it back. And you see that it is taking 4, 5, 7 nanoseconds for every instruction. So if we have 3 instructions, it will take 21 nanoseconds for the basic processor, for the basic CPU to execute this program. But when we are introducing pipelining, it's like that. We are saying that we are using some storage components between different stages inside the processor to be able to keep their result for each instruction. Then we can load more instructions inside the CPU. So if you see here, because we have different stages, we are going to make the working clock to produce pulse signals for the longest stage, because we are going to load them. We want to make pipelining possible. So this idea is that when the instruction 1 fetched and when it is in the decode stage, we can fetch, because fetch unit now is empty, so other instruction can use that. And based in this idea, we can fill our processor with more than instruction at a time. So in this way, you can see that the time may have increased for one instruction. It has changed to 1, 2, 3, 4, 5, 10 nanoseconds for one instruction. But because we are pipelining, it just takes 14 nanoseconds for 3 instructions. That compared to the 21 nanosecond in the previous scenario, it is better. It's nice. And this kind of parallelism that we are using, it's called implicit parallelism, because the programmer is not going to know about anything about pipelining that is happening inside the processor, inside the CPU, and it is called using instruction level parallelism. So now we got an idea about how CPUs, how central processing units are working and executing instructions. But when it comes to GPUs, it's better to remember that they are parallel processors. They are very good for throughput-oriented programs, and they are at lower working frequency compared to CPUs. If we usually demonstrate a basic CPU with this figure, that it is getting one instruction and one data, working on it and giving out the output. This one stands for single instruction, single data. It's how basic processors work. But processors offered some libraries and implemented in their hardware that it was making it possible for image processing, because like when we are applying some filters to images, we are going to apply an fixed operation on all of the pixels. So x86 MMX instructions that it is available in Intel processors offer doing one instruction on different data at the same time. That is like that you can keep it in your mind just by knowing how we are applying filters to images, doing one instruction on all of the pixels at a time. But when it comes to GPUs, each GPU core is a single instruction, multiple thread. It's like that we are executing one instruction from different threads. And how each GPU core is working is that it is executing one instruction from multiple threads, and also it's working on different data. This is the basic idea of GPU that offers a large parallelism, a big parallelism. So if we look at the schematic for GPU and CPU, it's like that you can see on GPU we have a lot of cores compared to CPU, but the cores of CPU are very powerful, they are very fast, they have larger memory, on-chip memory. But for GPU we have smaller, less powerful cores compared to CPU, and also less on-chip memory compared to CPU. As we talked about that this video will give idea to data science and people who are working on machine learning, deep learning models. Here we try to visualize how a CPU is going to run this training or this inference specifically for a neural network. And for each node, we know that this kind of multiplying the input to weights and then summing them all up happens, and then finally activation function is done on the final result. So for each neuron, the things that will happen is like this one, that the processor, that the CPU will go for the first one, then for the second, and this will continue until the final layer will produce the data. But for GPU, because it's parallel, the thing that happens is like that. It is going to launch many threads that they are going to work on the first layer. It will launch its threads that they are going to work on the second, third, and the final layer. And this is why the GPUs is going to work better in parallel programs, and neural networks are a very good example of parallel programs. And if we look at this video that it is produced by NVIDIA to showing the CPU and GPU difference,
all right, I introduced you Leonardo,
why GPU
and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed
This
it up.
machine represents CPU that even you are going to make it faster, the thing that happens is going to draw faster. But for
Ladies
GPU,
and gentlemen,
game is different.
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over.
This video shows
Thank
how
you.
different threads, how a lot of threads are launched at the same time compared to CPU that it was launching one instruction or one thread at a time. So we saw together the CPU, GPU and their difference, and we saw about how CPU was working. Now we reach to the FPGA, Field Programmable Gate Array. This device, this processor, was kinda used for prototyping by electronics people. They were using high-level languages like VHDL and Verilog, and also these days it's used, not they were using, it is used currently. These languages, these very low-level languages, are used to describe hardware that it is going to be connected on the FPGAs, and using these languages requires basic knowledge about digital electronics. But other high-level languages like System Verilog are possible for describing circuits. But the thing that happens here, we have to pay attention, is that when we are writing programs in Verilog or VHDL, as their name offers, HDL, hardware description language, we are not writing a program that we are expecting each instruction to be executed after each other. We are describing a hardware. We are describing a hardware that is going to be built, to be wired inside the FPGA. And Intel, after purchasing Ultra company, that Ultra was producing FPGAs, Intel is working on FPGAs, and in this specific chip they have integrated FPGA alongside a CPU. But how FPGAs work in the age of AI? When we are going to program or describe our hardware inside the FPGA, it's like that we are going to get our input from the FPGA's inputs. When we are getting them, they will fire because we have the hardware, we have our neurons, our program built inside GPU as circuits. So based on getting the input, they will fire. So it will execute like GPU, but in a more efficient way, because GPUs are going to schedule instructions, they are going to do more stuff to be able to compute for us. But this one, FPGA, and also you will see also Accelerator, they are not going to do more stuff to do computation, like scheduling, like writing to registers or other things. Because in this way, we are building hardware just for our specific program. But it is not flexible. It is hard from programming side. When you want to change the number of inputs, it's not like CPU, GPU to specify by number or change the program easily. We have to change these numbers and think about the other things that's happening on the hardware in the program. We have to tune everything ourselves. So the accelerator is the last processor that we are going to talk about. When we say accelerators, they are indeed application-specific integrated circuits, or ASICs, because they are built for a specific application. For example, if you have a specific hardware for processing sound, for example, you cannot use it for processing a general program, a general Python program, because it's not supposed to process that. You are not able. You have to do other things. You have to change your program. You have to translate to the language of that processor, and when you get output, you have to translate back to your language. It is like speaking to a foreigner. So it demands a lot of work and time to be able to speak to those specific processors. And in these accelerators, in these processors, everything is specified by the designers. How you are going to give inputs, how you are going to get outputs, where you have to store your data, where you are going to get your data in memory. All of these are specified by the designers, and no flexibility in being able to use them for other kind of programs. And the reasons for these accelerators is that we saw that GPUs were good at executing neural networks, but if neural network is getting bigger, our GPU saw that it was able to, for example, send this amount of threads parallelly to, for example, it was able just to execute this amount of threads, this amount of work at one single pace. But here our model is so large that it's not able to get all of them to get all of the layer 1 computation at one cycle. So it will take it at several steps. You see, even kind of serialization happens in GPU. But when we are building accelerator, we are building hardware specific to this processing, to this neural network processing, and the accelerator will be able to get this amount of input, do it at a one pace, one step, or two step, in a way that it is more efficient than GPUs or CPUs. And that's the reason why we move toward more specific hardware. And a good example of accelerators is Google's tensor processing units, that we have them virtually available on clouds. You can see when you are doing some computational Google Colab. The Google uses these devices in their data centers to offer more performance compute to CPU GPU. And another example is Serapha's wafer scale engine, that it is in this size compared to the largest GPU, and it offers a good performance to the deep learning neural network applications. So in this video, we talked about computation and how processors make this computation possible for us. We saw the trade-offs of different processors. We talked about basic CPU, how modern CPUs are sophisticated compared to the basic ones. We talked about GPU, FPGA, and finally we ended up with accelerators. And I would be glad if you have any questions and you are going to write it for me in the comments or send me emails if you come up with any question. Or if something was not clear for you, please write for me. I can make another video or write the answer or try to find the answer for you in the comments or respond to you later. Thank you for your attention.